Hello students, today we will discuss about defect modes in photonic crystals. So we have seen what you meant by photonic crystal. Now we'll see what are the defects. So you can have microcavity effect in photonic crystal. That is one another feature of photonic crystals. So what do you mean by microcavity, or how do you get it? So we can design micro or nano cavities embedded into the photonic crystal by creating defects into the crystal. That is, the defects could be dislocations or holes or anything like that. So you can tailor the size and shape of these defects. That means you can control what should be the size of the defect, and hence the microcavity of tunable size and dimension can be created. So these defect sites create defect associated with photon state. That is what you meant by defect modes. So defect modes are those energy modes which are possible for a photon due to the presence of any defect sites in the crystal. So these modes are generated in the band gap region. So these defect modes are actually analogous to the impurity states between the conduction and valence band of a semiconductor. As you know, when a pure semiconductor is doped with a p-type or n-type material, a donor level or a acceptor level is introduced between the energy gap region so that it can facilitate conduction. So similarly, the band gap, in the band gap region, a defect mode, which is the new allowed possible mode for or energy for the photon inside the within the energy band gap. Okay. So this is one such defect mode. You can see a new line is possible, line of energy is possible, which has been introduced due to the presence of defects or due to the introduction of defects in the photonic crystal. So these defects are spherical in shape. For example, if you have a packing of spheres to form a three-dimensional photonic crystal, if one of the sphere is missing in that assembly, then that spherical cavity is called a microcavity, which can support an optical mode. That means a new allowed photonic state or an energy state is possible for the photon, for which the diameter is given by d is equal to n lambda by 2, which means the lowest mode will correspond to n equal to 1. So it can be seen that as the diameter of the cavity is getting smaller, you can see the lambda will also get narrowed down. So that means the number of modes that is available will depend upon the diameter of the defect or the diameter of the cavity. So if the smaller the diameter of the cavity, smaller would be the modes. Okay. And there is another factor also which characterizes this cavity, which is called quality factor, defined as omega by delta omega, where delta omega is the spectral width, how much is the spread of the cavity mode. So for a photonic crystal, if it has high quality factor, which means a denominator has to be very, very small. That means the spread of energy or spread of frequency is less. That means low mode volume nanocavity. Spread is less means low mode is, or low volume or low diameter is there for the cavity. And hence, if the spread is less, then we can pinpoint to a particular wavelength. Okay, if the spread of wavelength is less, which means there is a particular wavelength that is being propagated through the band gap. So high selectivity of that particular wavelength is possible if you have high quality factor. Okay, so this enhancement of electromagnetic field within the cavity can be applied in devising light emitting diodes or low threshold lasers. So that is one application of having microcavity. Let us look into another various other defects possible in a photonic crystal. The first one is point defect. So the point defect means we are removing one sphere from the three-dimensional assembly, or if you remember, in the case of photonic crystal, we could make photonic crystal by arranging the rods parallel to each other, isn't it? So if one such the radius of one such rod has been changed from the other available rods, if it has become thinner rod, then it means there is some mismatching is there among the crystal structure. So that will lead to a defect state. Okay, so that is what you meant by a point defect. So in a point defect, we imply we are that is a colloidal crystal is there, or we are doping one of the sphere with a higher volume or a smaller volume compared to the neighboring spheres. So if you have a packing of similar spheres, if one of the sphere is bigger than the neighboring one, that will lead to a defect state. Or if the one of the spheres of the colloid is smaller, that will also lead to the defect state. So such kind of defects is called point defect. So so that will introduce a new allowed photon state within the band gap, and the frequency of or the energy of that new state will depend upon what is the radius of the rod or radius of or the radius of the sphere that has been changed. So such a point defect is called resonant cavity, which is formed by removal or change in radius of one of the rods. And another one is line defect. Line defect means we are removing one line of rods. That means if you have many number of spheres which is forming a three-dimensional assembly. Okay, so if one line of spheres have been changed, it is not about a single sphere or single rod, but the whole line of spheres or rods have been removed or changed, that will act as a waveguide. So that would allow the frequencies, a range of frequency to be allowed within the band gap. So that is analogous to p-type and n-type doping of semiconductors that introduce the new donor level or a acceptor level in the energy gap. So similar to that, if you remove or change one line of rods, then it can introduce a line defect, which means a range of frequencies are newly allowed in the band gap. So that is called waveguide. So what is the speciality of such a waveguide? So the waveguide would be like a pipe that confines the electromagnetic energy, enabling it to flow in one direction. That means if whatever be the direction along which the defect is there or line defect is there, that will act as the waveguide. So the light will be guiding through. So if I am removing this, so suppose this is an assembly of rods and we are removing this one particular line also, then what happens? The line defect will guide the light to confine or pass or direct along the cavity, along the waveguide along. So such kind of directing, that is a sharp bending, is also possible if you have such kind of a defect. So if you make use of a photonic crystal for guiding the light, then it can turn around very sharp corners, just corners, unlike the light traveling in a fiber optic cable. In fiber optic cable, the principle is total internal reflection. So if the frequency, if the angle of incidence is if the fiber is too much bent, the angle of incidence will not be sufficient for the total internal reflection to happen. So there is a possibility that light might escape from the fiber optics cable. But if you are using for photonic crystal, it cannot escape into the crystal. Why? Because the line defect is introduced in the energy band gap. So only along the waveguide the light will be able to propagate. It cannot move out of the waveguide, because moving out means it is a forbidden energy gap region, which doesn't allow any light to propagate. Okay, so that is how the light will be confined within the waveguide, which is due to the line defect. So there is a depiction of cavity as well as waveguide here. So here you can see the light is getting trapped inside a small cavity which is due to the point defect, while you have a line defect where a line of spheres or rods have been removed, which will act as a waveguide. So the light will be confined to travel within that waveguide alone. It cannot escape from that waveguide. Okay, so in the point defect, what we are making is, we are actually making some cavity, and those cavity will be depending highly on the radius of the defect. That is, whatever be the radius that been changed, that will decide the energy state of the cavity. So if the diameter is of the order of 0.0, radius is of the order of 0.05, then you'll get a cavity in the range something around 0.36 range. If the cavity is having a radius of the order of 0.1, then you'll get a frequency mode something around 0.325. Okay, so the energy of the cavity will depend, or the frequency of the cavity will depend highly on the radius or diameter of the defect. While in the case of line defect, so in the case of point defect, we can tune the frequency of the cavity, and the ability to tune the light and concentrate it in small region gives the photonic crystal a potential for use as filters and couplers in laser. So this will act as a coupler or filters in laser. While in the case of line defect, you can see this is the forbidden energy gap region, where below is the dielectric band and above is the air band, and you are introducing a new allowed energy in the energy band gap. So which means the light can propagate through this waveguide. Okay, that is an example. So here you can say a colloidal photonic crystal is represented, where it is constructed using an assembly of many number of spheres forming a three-dimensional photonic crystal. So if one such sphere is removed, or one such sphere is having a different diameter, then that will lead to a defect state. And as we mentioned earlier, the waveguide or the line defect state can be used for optical communication purpose, where you can channel the light through the defect region along. So guiding through the well-controlled defect channels allow sharp bending of light without any loss. So here you can see this is the region of the waveguide, and the light is propagating along the waveguide alone. It is not moving out of the waveguide. It is highly directed through the channel of the waveguide. Okay, so a 90-degree bend can be clearly visible. So this is another depiction of how the light will be bent along the waveguide. So here you can see one can make these defects in different topology. Whatever be the waveguide nature you require, you can make it in that way and guide the light. So the application of photonic crystals are waveguides, which will enable sharp bending around the corners, unlike the optic fiber. And another application is resonant cavity can act as a coupler in lasers, which means it can control what is the coupling between the atom and the photon. That means it decides the size of the cavity will decide what is the energy mode that is possible. So the density of electromagnetic mode within the cavity, as well as how much is the coupling between the atom and photon, can be controlled using controlling the defect state. Okay, so that these two factors will decide what would be the rate at which an atom can decay. So the decaying of atom from the excited state to the low energy state is very essential for the lasing action to happen. So the presence of resonant cavity, tunability of the resonant cavity can help in producing laser action. And the third application is photonic crystal can be used in integrated circuit as well, because the light travels, as you know, the light is the having the most velocity compared to any other particle. So it can travel much faster in dielectric medium than an electron in a wire. So it can carry much more information per second than the usual. Electrons are the carriers in the computer system, right? So instead of using electron and semiconductors, we can make use of these light and photonic crystals, where the light will act as the information carrier. So then you'll get a frequency range of terahertz, that is 10 raised to 12 hertz frequency, while the current system using the electron has 100 kilohertz. So a better processing speed can be obtained if you make use of photonic crystals in integrated circuits. So that ends the chapter on photonic crystal, where we have seen what is photonic crystal, what are the features of photonic crystal, what are the different types of photonic crystal, and lastly what are the defects and corresponding applications of photonic crystal. Thank you.